Right, here we've got an electron being fired from an electron gun, accelerated. Here's its mass, and it goes to the speed of this, and it goes through a crystal. Now a crystal is like having a double slit, but in 2 dimensions. So instead of just getting bright band, dark band, bright band, dark band, bright band, dark band, you get a 3D interference pattern. But it's the same principle as light going through a double slit, and because an electron has wave properties, you get this interference pattern of bright, dark, bright, dark, bright, dark. Depending on the arrangement of the atoms in the crystal, that's what the different why there's bigger bands of darkness for some of them. Alright, calculate the de Broglie wavelength of the electrons and show your working. So the formula for the de Broglie wavelength is P equals h over lambda. So rearrange that, you get lambda equals h over p. That's what we want to use, but we don't have p. We've only been given the mass and the velocity, so we have to do that first. So p is mass times velocity. In this case it was 9.1 by 10 to the minus 31, and the velocity was 1.5 by 10 to the positive 7, and that gives 1.365 by 10 to the minus 23 kg ms negative 1, and then we use this formula here, h over p. The Planck's constant we use is the 6.63 by 10 to the minus 34, 1.365 by 10 to the minus 23. That's from up there. You do the calculation there, and you get 4.9 by 10 to the minus 11 meters. Alright, they want the answer in nanometers. Now this, a nanometer is 10 to the minus 9 meters. So this is smaller than a nanometer. So hopefully our answer that we're going to put down here is smaller than a nanometer, like 0 point something. The way I'm going to do it is I'm going to do it one step at a time. I'm going to say, what is this as opposed to in by 10 to the minus 10 meters? Well, it's 0.49 by 10 to the minus 10, because this is smaller than a 10 to the minus 10, so this number must be small. The dot decimal point must go this way. And now do the same thing to get it into a 10 to the minus 9, because that's what a nano is, so the decimal point moves again. There we go, so that's the 0.049 nanometers. That was question 7, we've got question 8. Okay, students now increase the accelerating voltage and hence the speed of these electrons. Which of the options shows the best pattern they will observe on the screen? So the velocity is going faster. Okay, and this is just like a double slit. You've got to explain your answer as well. So in a double slit, the thing that'll change it is the wavelength. So how does the wavelength change is what I want to talk about. So I'll put my answer last, as I don't know what it is yet, but this is what the working that I'm going to go through is that the velocity increases. P equals mv, so the momentum increases, and a wavelength equals h over p. So if you have p goes up, lambda must go down, so the lambda decreases. Now this is something you might want to have on your cheat sheet. When lambda goes down, the fringes get closer, and when lambda goes up, the fringes get further from each other. We've got lambda going down, it's decreasing, so the fringes get closer. So that if the original pattern was B, the fringes get closer to each other, so that must be A, the answer A. And the reason that is because if you imagine the double slit, you don't have to write this down, but this is just for your own understanding. This is kind of like a double slit. Here's your screen. If you're looking at something over here, remember we talk about the path length to here and the path length to here. And then we talk about the path difference between them. If you have a, so the path difference is the difference, and if you take those two arrows and you put them beside each other, there's the top arrow and there's the bottom arrow. The path difference is this difference here. If you have a smaller wavelength, here's a big wavelength and here's a smaller wavelength. If you have a smaller wavelength, you can have a smaller path difference in order to have bright spots, bright spots, bright spots. Okay? A smaller wavelength means that these arrows can be much closer in size to get another bright spot, which means you don't have to go as further out to get that path difference. So you can get the fringes closer together. That's something you might want to get your teacher to talk about better than me. I don't think I've done a particularly good job of explaining this little bit here. But in terms of getting the right answer and putting down the working, this will be enough to get the marks. The next question is question 9. Right. Figure 5a, this one here shows the diffraction of electrons, 600 electron volts, and now they replace the electron gun with an X-ray source and they observe this pattern, which is very, very similar. Explain why X-rays and electrons have this similar pattern to each other. How much is this worth? It's worth 2 marks, so yeah. Well, the reason is because both electrons and X-rays have wave properties. Oopsie. Have wave properties. And in this case, so that was why they both make an interference pattern in the first place, but in this case the interference patterns look like they're the same size. So both electrons and X-rays have wave properties. In this case, the electrons and X-rays have the same wavelength. So that's why they are they have the same size interference pattern, because they have the same wavelength. It's going to be helpful for the last question in this series. Alright, question 10. So I've just copied and pasted that same picture, so we've got enough information. And question 10 is asking us, estimate the energy of the X-rays in electron volts of the X-rays. Now this is a really hard question in terms of how many students actually got it right. It's quite a bit of working just for 3 marks. So I'm going to do a plan of my working and then we'll go through and do the working. Alright, remember here's our diagram, and we said they were the same pattern because they had the same wavelength. That's the key. And we've given the energy of the electrons in electron volts. So my working, and we're going to do up here, well, this is a plan of my working. They've given me the electron volts of the electron. I'm going to turn that into joules. Then, from that energy in joules, I'm going to find the momentum. And from that, I'm going to find the wavelength of the electron. I know that's equal to the wavelength of the X-ray, and from that wavelength of the X-ray I'm going to get the energy in joules of the X-ray, and that's not equal, so that's going towards that, and then from that I'm going to get the energy in electron volts of the X-ray. So a huge amount of working to get through to this answer. But let's go down and get it all down. Again, I don't know how much space. We don't have enough space really to do that either. But I'll try my best to fit it all in. So again, we'll follow this and we'll get there. So 600 electron volts. The first thing I was doing was going to joules. So to do that, I have to divide by 1.6 by 10 to the minus 19. And that equals 9. Sorry, if I'm going from electron volts to joules, I need to times it. Times it by 1.6 by 10 to the 19, and that gives 9.6 by 10 to the minus 17 joules. That's that first step. What was I doing after I put it into joules? I was going to get momentum. Now I'll do the working up here. Energy equals P squared over 2m. So if I want to find P, this is for going from joules to P, P must be, I times both sides by 2m, and then a square root. Okay? So P equals the square root of 2me, which equals, I'm not going to fit that there, I'll put it down here, equals the square root of 2 times 9.1 by 10 to the minus 31, the mass of an electron, by the energy I've just worked out, 9.6 by 10 to the minus 17, which equals 1.32 by 10 to the minus 23. Alright, we've got P. It's just, so people know where we're going. We're going here, we're going here, well, then we're going to go over here. We now want to find, after we've done P, we want to find lambda. Lambda of the electron. So lambda of the electron equals H over P. There's our arrow, we go to that. There's our P equals that, we now go to that. Which equals 6.63 by 10 to the minus 34 divided by my P, which is 1.32 by 10 to the minus 23. A lot of working. 5.01 by 10 to the minus 11 meters, and that equals wavelength of the electron equals the wavelength of the X-ray, which equals wavelength of the X-ray. Alright, we're getting somewhere. From the wavelength of the X-ray we can work out the energy of the X-ray. Energy of the X-ray equals Hc over lambda. Equals, let's just divide this up here so they can see this is separate. Which equals 6.63 by 10 to the minus 34 times 3 by 10 to the 8 divided by lambda, which we've got 5 by 10 to the minus 11, and that gives 3.97 by 10 to the minus 15 joules. Alright, we've got the joules, now we're going to put it in electron volts because that's what they want our answer in, and to put that into electron volts we divide it by 1.6 by 10 to the minus 19, which equals 784 electron volts, which is our answer, which we'll just round off. 248 electron volts. Very, very tough. Not much working space to get that all on. I hope they can follow it. I hope you guys can follow it as well. Make it a lot easier if we had this up here, so maybe that's worth putting up as part of your working as well.